Okay, now I'm going to talk about another kind of vector product in addition to the dot product that's going to be very useful for us. So I'm going to put the dot product identity off here to the side so we just can remember it and we're going to compare it to it. But there's another product we're going to talk about called the cross product. So the dot product took two vectors and the multiplication actually ended up giving us a scalar, right? Just a number, not a vector, whose magnitude was, or whose just number was the magnitude of u times the magnitude of v times the cosine of the angle between the two vectors. And we talked about another product, which was like the component-wise product of the vector elements that actually did give us back a vector, and that was like light reflecting off of some surface. But there's another kind of product we can get that takes in two vectors and actually gives us back a vector. And it's a little bit more mathematically useful than that. So, and that's the cross product, as I said. And so it's denoted by this times sign. And what it ends up being, actually it's only defined for 3D vectors. So let's say that u, I'm going to get sloppy with the arrows because they take me so long to write, but u is a, b, c, and v is d, e, f. Okay, so then the cross product between u and v in terms of those coordinates is, it's actually a vector, not a scalar, so we're going to have an x, a y, and a z. So the x is going to be b times f minus c times e. The y is going to be c times d minus a times f. And then the z is going to be a times e minus d times b. Now where the heck did that come from? What is that? Well, so it turns out what you can verify is this cross product identity. So this is a vector, but its magnitude is equal to, so the length of this vector that I get from doing this weird thing is equal to the magnitude of u times the magnitude of b times the sine of the angle. So the magnitude of this vector looks a lot like the dot product, except for instead of a cosine, we have a sine. And this has a nice geometric interpretation as well. So we saw that the dot product identity was pretty close to a projection. This is actually going to be a little bit like an area. So in fact, it is an area. So actually, okay, so let's say that this is our vector u here. Again, so I'm just going to draw this setup and we're going to try to understand the geometry. So that's my vector u. And then I'll draw a vector v with the same endpoint. So same origin. And we will again say that the angle between them is theta. Oops. So here we go, there's our theta. All right. So I'm going to do the same thing, and I'm going to drop a perpendicular because I want to deal with this right triangle again. But this time, instead of looking at the cosine, which was the adjacent, I'm actually going to look at the sine. So this here is the magnitude of, really the sine is the magnitude of, so magnitude u times the sine of the angle is the magnitude of the perpendicular projection. But actually what that is, okay, so I'll write that there. So this is the magnitude of u times sine of theta, right? So that's just the definition of the sine there. Okay, magnitude of u times sine theta is this length here. Now, let me actually draw, okay, so that is the height of this triangle, right? And the base of this triangle, well, okay, so I haven't completed the triangle yet, but here it is. So that's our triangle. And the base of this triangle is the magnitude of v. Okay, so the magnitude of v is the base. And remember that the area of the triangle is 1/2 base times height. All right, so I can say that, okay, so this is the length of the height. Let me actually write that. So height is u, magnitude of u times the sine of theta. And then the base, let me not write h and b since I already used b. So the height is magnitude of u times sine of theta. The base is the magnitude of v. And so 1/2 base times height, which you should remember from high school at some point, hopefully, That's going to be magnitude of u. That's going to be 1/2 magnitude of u times magnitude of v times sine of theta. Okay, so we see that 1/2 of the magnitude of the cross product is the triangle area of a triangle that's formed between the two vectors v and u and v. And this is also amazing because these vectors are in 3D. So now this allows you to figure out the area of a triangle in 3D from 3 points. So you can, if this was a point here, like A, and this was a point B, and this was a point C, well, I'll just construct the vector u, which is C minus A, and I'll construct the vector v, which is B minus A, and I'll take u cross v, take the magnitude, and then half of that is the area. Another way of saying that is that actually, if I go back to think about vector addition, I actually form a parallelogram if I add u to v or v to u, and I end up with this parallelogram. Actually, what this is saying is if you make that parallelogram, the magnitude of the cross product will be the area of that whole parallelogram. So in this parallelogram, you have two triangles with equal area. Each one has this area, 1/2 magnitude of u times magnitude of v times sine of theta. Okay, but I got two of them, so I multiply this by 2, and I'm left with magnitude u times magnitude of v times sine of theta. So nice. Okay, so we can actually use the cross product to compute areas. And that's extremely useful. So that's one of the tasks on the homework. That's the third one, right after projections, is to figure out the area of triangles. So now you know enough to do that. But I want to also think about the direction of this a little bit. So I've told you something about the area, but I haven't really analyzed the direction. So I want to have you do an exercise real quick about the direction of this vector.